Any questions for physics or non-physics related? Any questions so far? No? Okay.
So, does we have a winter test?
If you want.
Oh,
Okay. So then no. But you might have a final exams. Okay, any other questions? Okay, good. So let's get started and finish what we started. Finish. So we start talking about the symmetry, and then we were talking about Euler theorem. The statement was if there exists continuous symmetry, then there exists a conserved current, right? And for Lagrangian theory, we actually derived the expression for the conserved current. So that was in general looks like where the d of phi was defined as if field transformed as delta phi with some small parameter epsilon, we define the location according to this expression. The f hat was defined in such a way that if Lagrangian overall shift like total derivative epsilon f me. Okay, so that was the Euler's current. All right. So then we talked about space-time symmetry. So in particular, we talked about translation, space-time translation. Right? So there, this is a quick summary because it was more than a week ago. So for translation, we consider x mu going into x mu plus some small parameter again, and then e mu. If this is a unit vector pointing some particular direction, this basically, quantify the size of the translation we are taking. And then we said that for each translation, in this case, there exists 4 independent translations. There should be a current that carries only a single space-time index mu. So that means that for each transformation, there should be some tensorial object that looks like this to make a correct, if you like, I can put down. Right? So for each translation, we do have this conserved current, therefore there should be something that looks like this, which is known as energy momentum tensor. And we even derive this energy momentum tensor by explicitly working on this part of the exercise, right? So energy momentum tensor, let's use the same notation, looks like mu, and then we did the rho g from mu, and then what, like right? So that we derive. So we call in particular this is canonical energy momentum tensor. Energy momentum tensor. And then I also discussed that while so from once you have conserved current, one can define a charge. Now this is a charge which is defined as integration over space, then zero component of that. And then we talked about 2 conservation laws. One that looks like a local conservation law we talked about, and then another conservation law that is derived from the local conservation law was this should not change under the time evolution. Okay, so the picture is that if there's a time they're flowing like that, in a more general sense, then one can slice out the time. So one can define one time slice, which is like your space. So let me call that first slice as sigma 3. Then one can define a charge by integrating 0 component of the current over the entire space. And then therefore there's a particular time attached to that. So then one can pick up another slice that we call sigma 3 tilde. And then one can also define a charge. Then the global version of the conservation law states that the charge overall should not change. That's the same. And I told you that this may contain more information because this is validated at each space-time point in the board. So if by looking at every point, you must satisfy that property, right? That was the discussion. Okay, so and then we also evaluated how does it look like. Well, once you have that, the zeroth component does have a p of a row 0. So we looked at integration of p of the row 0, and we call that p row, right? Which makes sense because eventually we want to define a Q, so that already has integration over that part. And we show that this is nothing but by actually looking at it, Hamiltonian, and then so I think it's probably that's the discussion we had last time. Okay. So far, any question? Yes.
Is the P the same as the momentum generator and the Poincare algebra?
Good. So I'm going to talk about a little bit about that. The answer is, so at this point, we are talking about the classical physics. I have not really talked about the quantization, but the answer to your question, which I will get to, is that, so we derive this momentum function, which is a function of a field, okay? Which is a function of a field. So these are all functions of a field. The function of, therefore. So we can quantize this thing, right? So we can pass from the classical theory to the quantum field theory. We can quantize this thing, that this will be promoted into the quantum operators. And then we can show that those quantum operators indeed generate the symmetry transformation acting on the field. So in that sense, indeed, that is the generator of the Poincare algebra that actually performing space-time translation on the quantum field in the universe space. In that sense, the answer is yes. But I'm saying there's a little bit more steps to go because there's quantization and then to see how that actually comes about. Any other question? Good. So that was the quick summary of what we talked about. Let's now move on to Lorentz transformation. So I'm sure you all remember every single detail of the Lorentz group that we talked about, right, at the beginning of this course. Okay, so the answer is no. So here's a quick summary. So we talked about, so what is the Lorentz transformation or Lorentz group? Given a metric, you know, then you have transformation acting on it, and which leaves metric area. And any such lambda is defined to be a Lorentz transformation, right? It's isometry. And then you can expand this guy with 1 plus small thing. So just write it epsilon times nu. So again, I'm writing the notation in such a way that this, it's just like this E vector is not necessarily a small vector, it's just a unit vector, and then the small is calculated by epsilon. I'm just writing the same way. So I'm just expanding the lambda 4x4 matrix from 1 plus small quantity, but I'm not saying that the omega itself is necessarily small quantity, but I'm just putting in this little epsilon factor to control the size of it. Okay, and then by plugging in, you remember that this is antimetric, the sense of this expression. And then we also talked about the fact that given this space-time transformation, we can have associated quantum unitary operator that acts on the Hilbert space, in this case, Fock space. And then in the case where I consider small, transformation, we talk about the fact that this can be expanded as a unit operator plus I over 2 omega mu nu. In this case, I have to put epsilon 2 j mu. Right? So we expand it to linear order. And then again, from the property that this is antisymmetric, this must be antisymmetric. And then the fact that this is unitary implies that this should be permission operator because I put I there, right? We talked about all this. So now let's use this fact to talk about the Noether department and associated departments. Okay, so Okay, so then what do we expect? So let's first think about what do we expect. Before we actually work out, right? By which I mean, according to this line of reasoning, what do we expect? In the case of translation, there were this vector value parameter. Therefore, we knew that there should be some tensor that looks like this in order to generate the conserved curve like this, right? Just based on the Lorentz property, Lorentz symmetry property, we knew that. Let's do the same thing. Here, transformation parameter is this antisymmetric tensor. And then yet I need to get the conserved curve out of it, right? For each continuous small transformation, I should get vector values conserved curves. Which means that there must be a tensor that more or less looks like this. Vector of out being which I will explain. Right? So forgetting about this for a second, because for each transformation I must have a conserved curve, I know that there should be some tensor that looks like this. Right? In such a way that this thing is antisymmetric with respect to the first two indexes, because it is antisymmetric. Now you can also understand why factors of 2 there, because if you just work it out, for instance, 1, 2, and 1, 2 mu, and then this will also have a 2, 1, 2, 1 mu. But by antisymmetric, this is the same as 2 times 1, 2, 1, 2 mu. So there's a redundancy, right? So I'm just dividing by 2 just so that it only has a single factor of each one. Right? That's the definition. So the question is, who is this guy in terms of field theory? A quantity. In terms of quantum field, what is that tensor? So let's construct that. So what is the systematic to follow? How do I determine that thing? Well, you already know that because of the expression I just erased. Right? So the conserved current, in order to figure out the conserved current, you need to just basically work on 2 quantities. Right? One, well, you have to know this, first of all. But in particular, you have to figure out how field transform under Lorentz transformation. That's the first thing you have to figure out. The second thing that you need to figure out is how Lagrange shift, right? Under Lorentz transformation. So let's again consider the infinitesimal transformation. Lambda, in other words, x goes to x prime, which is lambda times x. Right? This is Lorentz transformation. And then I consider the infinitesimal transformation, which is epsilon times omega x. So let's now put the index back to understand what I mean by this. Right? So by which I mean x prime rho is equal to, just putting back the index, x rho. Epsilon was just a number, small number. Omega rho mu x. Right? Okay. But now, in order to actually work out this, remember, given a field of x, the way this guy transformed the Lorentz transformation was u diagonal lambda. Yes. Is equal to what? That was prime. I'm dropping the. That was how this thing transforms. So you may have forgotten where they come from. So let me quickly remind you, right? So given a state, they say P state, we knew that this guy transforms like that. Right? So this is how we knew that. So now if I consider acting on some field, it can be this or something else, acting on that. But let's again consider how that acts. So Lorentz transformation acting on the state like that. But then this can be repackaged in terms of u vector phi or x u and p. So what I'm saying is, you can think either the state transform in the Schrödinger picture and operator doesn't, or you can view that as if state doesn't change, but operators transform. right? So that's a Heisenberg picture. So what I wrote here is Heisenberg picture, but then I also explained the argument change opposite way. Because, for instance, if you had a function that is localized at 0, and then you do the translation such that it's now localized at x equal to, this is f of x, and then you want to have a function that is picked at x equal to a, then but you have to have argument in x minus a, because the 0 of this argument corresponds to x equal to a, right? So it goes the opposite direction. So that's why you have lambda inverse of x. Okay? Good. So with this reminder, then let's see. Now we are ready to evaluate these two factors. Okay, so let's see. So in the case of scalar, which I'm considering now, okay, if you were spin the particle, spin the field, actually there's something more in front of this. But I'm just talking about the for now scalar. Okay, we haven't developed the machinery to talk about the spin of field, which we will. So let's work this out. So if lambda is 1 plus epsilon omega, is it this small by the way? That can you see from the back? This is okay. Lambda inverse is 1 minus epsilon omega to leading order in epsilon. Okay, because you just product of the two is it becomes 1 up to order omega squared or epsilon squared. Okay, so that means good. So now we are ready. So phi of inverse of x. So that thing is, so let's first work it out. So inverse of x, that is what? X minus x. Yes. Again, let's put the index back. So if I want to say that this of the row, this of the row, that being of the row. So that means that x of row minus epsilon, row mu x. And if you like, you can do all sorts of things. For instance, I can just change the height of the mu because Lorentz index I can just go back and forth together. But then I can also make use of the fact that epsilon is antisymmetric in those indices to make the plot of epsilon mu rho x of mu. Whichever way you want. I'm just showing all possible expressions that you can keep track of minus. Here I just use the fact this is antisymmetric. Anyways, now let's work out the field. How field transform in order to read out this diverse. So phi of this thing. So let me just use this final version. So that thing can be written as what? Like x plus omega x. Again, remember, I'm just solving this checked expression when it comes to Lorentz index structure. All right. So that is phi of x, because this is infinitesimally small. And then this is like what? Shifting a little bit, right? This is a little bit of a small translation, but that is proportional to the x. So this is a spatial version of the translation. You know how to work that out? By Taylor extension, you can work it out. Rho phi rho. So again, by which I mean phi of x, omega x. Okay, so now we figured out the d of phi. Okay, so that's how field transform. Now note that this is a special kind of translation as I tell you. But remember, Lorentz transformation includes either space rotation or boost. Right? Once again, this guy is antisymmetric. It has 6 independent components. Remember that. 4x4 antisymmetric matrix has 6 independent components. 3 of them are space rotation, 3 of them are boosts. That makes it temporal and the spatial component. Okay? And then you have to convince yourself that this indeed can create a rotation, even though the way I wrote that is as if it is a translation. Probably I demonstrated last time. So let me translate here this much, small x. But let me translate the same thing, but it's proportional to that. Let me translate a little bit more, and then a little bit more. So eventually, it just create an image of a rotation. You can do it. So here, the fact that it's proportional to x is critical. That it can actually create a rotation rather than just linear translation. All right. So with that, now I figured out one thing. What about the change of Lagrange, which I need for this? That is expected to do thing too, because Lagrange at the end of the day is a function of x. But now I'm just doing lambda inverse of x. But that is exactly the same exercise that I need to do here, right? If I'm given a function of x, do the Lorentz transformation, I just need to follow the exact same thing. So I know that this thing is going to be epsilon omega mu rho x mu derivative of Lagrange. Right? That's literally copied what I said. But then what I need is I need to be able to write this as the total divergence of epsilon times f at mu in order to read all this f at mu. Okay, so let's do it. The claim is that this can be written as this epsilon oops. And then I need to compensate by G U rho. So let me see if I'm right or right. So I claim that this is the same as that, so that I'm ready to read out that. Let's check. I just wrote as if I just don't worry about the action of derivative acting on this and that, right? That's what I wrote here, right? I just put the derivative out of the expression. Let's see why. So this is a constant because I'm making a global transformation, which is independent of this. Yes.
Professor, I think there is four index.
Oh, good. Yes. Hold on a second. If I pull that out of it. Okay, so the reason why that is, so there's a dummy index. Dummy index. Now you're happy? We're still not happy. You're not happy, right? Okay, let me write it again. So let me just pull that out. First, let me just write. It's the this I claim is the same as omega mu rho x mu Lagrange. This has at least the correct index structure. Okay, good. So let's first check this is true. So this I claim this is equal to that. Why? So first of all, again, I'm making a constant transformation, meaning all the parameters are constant, so therefore action of that thing is nothing. Right? Next, if I act by this, so that action gives me G rho mu. Right? Because remember that is the same as x mu divided by x rho. Okay? So this is either 0 if mu and mu are not the same, or 1. 1 in this sense. So it's metric. Or you can just write it as x alpha G alpha mu rho, that is delta alpha rho, and then you contract, you get this metric. All right? So now this is symmetric, and that thing is antisymmetric. So that's 0. Okay? The contraction of antisymmetric and symmetric transfer vanishes. Okay? So that's why, for non-trivial reason, I can just pull that out. Finally, I can write this thing as if it looks like this. So let's do it. So for that matter, just for a second, I'm just gonna use the dummy index variable, replacing u with the nu. Okay? Because I decided to write it as the nu. Okay? So now what I can say is that I'm acting with that, but I have to go back to this, which I can do it if I do it with the mu contracted rho. I think I probably masked the up and down index somewhere. I mean, I can just do that way too. I mean, like that. Okay, so if I do that, instead of this, I will get just a matrix, but anyway, that doesn't matter. And then you have all this thing. New row, do, like that. Okay, so therefore, now I also know the F hat. So let me just collect all those two information together and write out the curve. So we just worked out these two. Now, which theory am I analyzing? I'm also thinking of a free theory of scalars. Just for the sake, but we can consider other theories too. But just for the sake of, I'm just going to consider this. So if I do that, then my current. Let me first write the general expression without worrying about which exact theory I'm analyzing, because I can just write it out if I just don't write explicitly this. So let me just keep it as this. And then I show you what this is. So that is equal to omega u rho x mu. Okay, again, let me just use nu so that I don't crash with the mu that I was doing here. And then rho phi, so that's that. And the F hat is again stripping out the epsilon factor. That gives me u rho, Lagrangian. And there are common factors. So this combination is common. I can pull it out. So they can be written as u rho x mu times and then I have this minus this. Okay, so far so good. There has been some technical steps to follow. But anyway, if you believe these technical steps, which hopefully it was clear enough to follow real time, then now we can look at it and think about the physical meaning of that. Let's do it. All right, I'm going to pause for 3 seconds if there's any questions or anybody needs any clarification so far.
No, in no A on 5.
Here?
I mean
Here? Yes, okay, let's put that in. If there's only a single phi, I don't have to put anything. I'm just here, I'm assuming there can be multiple phi's of this footing. Okay, yes. Okay, any other questions so far? Good. I just did technical calculation to determine this. All right. Now, what's this? First of all, one thing that I can do immediately is I can rewrite it as follows, just for the sake of it. Let me just lower and raise index like that. Let me just lower that into the price of raising these two. Okay, let me just do it. Again, I'm just gonna do this and then lower the row, raise the row, raise the row. That's what I'm gonna do. Okay, it's trivial Lorentz invariant operation, right? So if I do that, they will look like new row x new of okay. So this is the I didn't need it to, but this will make a more direct contact to what we have already determined. So now, hopefully, some of you recognize this expression in the parentheses as what we already determined before. So this is analytic momentum, the canonical version of analytic momentum test. Do you expect that? Do you expect to see such a thing here? Well, at least you saw a clue, right? Because Lorentz transformation is sort of a translation at the level of infinitesimal transformation, but with a specific parameter, which also involves x in it, right? So in that sense, you might expect that. Now, but then remember at the beginning, we also said that we expect the following structure. So mu, because for each transformation parameter, I want to see some vector current, which should therefore have some tangent that looks like this. And then we also talked about the 1/2 in such a way that we just avoid the double counting. Right? Now let's recast this expression that looks like this. So this is the one hand. On the other hand, we just have new rho x new t rho mu. Or if you like, I can rewrite this as okay. Let me not. So now I can write this as follows. That is antisymmetric, so I can write it as half of x nu. So I'm just antisymmetric these two. U minus rho t nu. Right? Because the second expression, by colliding with the antisymmetric tensor, is the same as the first one, so I'm dividing by 2. Because the original expression had only one vector of that. Okay? Good. Now by comparing this, now you can immediately read out. Okay, m alpha beta mu is therefore nothing but x alpha t beta mu minus x beta t alpha mu. Good. So we have determined this tensor explicitly for a given field theory. Good thing about this exercise is that I have not, for instance, specified exact what theory I'm using. This expression is true, right, for any Lagrangian field theory. So just like we did, so before what we have done is that therefore, just like, so now we are going to consider a charge. So this is the current. This is the current. We are going to consider charge. So we're going to take a look at the zero. And previously, in the context of translation, we just considered the integration of that with the 0 here, integrated over the space, right? We talked about that. Let's do the same thing here. So we're going to look at the object, which is integration over space, here, and then m alpha beta 0. So let's look at that. And this better be called something like j of alpha beta. And let's write explicitly. So that is x alpha t beta 0, x beta t alpha 0. Now, there was a physics meaning of this expression, remember. So let's recall that. By the way, there are a lot of indices, so you may get trouble because it's hard to keep track of all those indices. Sometimes just the expression itself can be an obstruction to extract the physics meaning out of it. So let me just take a pause to explain. If I do make that transformation, which are captured by this label, I have conserved current. And then zeroth component of that thing is called a charge density. And then the spatial component is the actual current. Right? So the mu tells me whether I'm talking about the charge density or the current. Alpha beta tells me which transformation I'm performing. So here now, if you look at this, the first index tells me which transformation I'm performing. And as a result of that, which conserved object I'm looking at, whether I'm looking at conserved charge density or current. Okay, so there's a lot of indices, but each of them has a separate meaning. All right. So okay, now let's go back it and then understand it. So remember the t mu also had a meaning. So in the context of a translation, remember each translation I want to have that again I'm performing translation and then I get either charge density or current, right? So in that context, remember therefore the zeroth component, which looks like this, looking at charge density. And that charge density, if I integrate over this gives me charge, which we call P mu, right? Momentum. So if I perform temporal translation, I get Hamiltonian as a charge density. If I perform the spatial translation, I get momentum as a charge density. Because I'm looking at the zeroth component of the conserved current. Okay, let me say it again. Zero charge density, I current. Under what transformation I'm making? So if I do the same thing, if I make temporal translation, which means that this I'm looking at the zero here, or associated charge density, or charge in this case, is a Hamiltonian. If I make spatial translation, whose charge is momentum? Okay, good. Now let's do the same thing for this vector transformation. Now we have some more indices, but nevertheless we can do it. Let's do it. So now therefore you convinced that this can be called as full momentum density, because if I integrate over the volume, I get the full momentum, right? So just like there's mass density or charge density, this is charge density, this is charge. So this, if I give a name, this is what's called momentum density mu. Okay? Which I get momentum I integrate over the entire space volume. So let's come back here, let's write that expression again. Momentum density beta minus beta momentum density. Okay, so that expression is useful because now you can look at, for instance, ij component, space and space, meaning by which I mean I'm making omega ij transformation. And if you recall, this is 4x4. And then if you pick both space and space, that's mixing space with space, that's rotation, right? If you pick one time one space, you're mixing time with a space, that's a boost. So let's first consider space and space, which is the spatial rotation. Let's ask what is associated with charge for spatial rotation by picking space and space. That gives me like xi pdj. I'm just rewriting. There. But what is that? That is literally cross product of r with the momentum, and then summing entire contribution of the field. So this is angular momentum, as you would expect, right? So now you can look at also this component, which is less layer, t with edi minus so xi, and then 0, so that's Hamiltonian. Anyway, I can write the expression, I can give some meaning to it, but nevertheless, this is the charge associated with spatial rotation. This is the charge associated with the boost transformation. So this is called angular momentum, this is called blunt. It is what it is. But I can give you more basic context. What those things are to you. Any questions? Okay. Good. So at least now you should be able to operationally derive all these results by actually working out line by line. Now let's talk about some more aspects of the symmetry. Okay. So the next thing I want to talk about is two important aspects of the symmetry, which usually does this is not discussed at this level of course, but I thought it better be discussed now so that you have a overall picture about the symmetry. So far we've been talking about classical aspects of symmetry, right? So classical symmetry it applies to control current, and we talked about a lot of them. Okay, especially space-time translation, and then Lorentz transformation, and we will also talk about internal symmetry soon. However, there is a quantum aspect of it. So there's a quantum aspect of the symmetry. Just like here, there is in terms of mathematical result known as Noether's theorem. Okay, so that we use to derive quantum current. There is a quantum version, there is known as a word identity. We are not going to derive this today. I'm just going to write down the expression for you. Because deriving this requires more technology that you have not learned so far, known as a path vehicle. Okay, so we will have to wait a little bit. But in quantum field theory, so just to state the fact, in quantum field theory, the key interest is going to be what's known as correlation functions. You may have a lot of instruments. So this is a vacuum expectation value of a chain of operators after you quantize the theory. But there's a weird symbol known as the time order. Let me explain what that means. Time ordering. So you remember that we talked about normal ordering. Normal ordering says that I don't care. Just to put the annihilation operator to the right. Is that right for you? That's right for you. Yes. And then put the creation to the left. Right? That was the dictatorship. Do it. So here time ordering is that order the stuff according to the time. All right. So for instance, here's an example of time ordering. So this is the vacuum expectation value. First, let's look at the 2-point function. So this is called 2-point function. If you have n operators there, it's called n-point function. This is time ordering. What does that mean? If time of x is larger than y, but this is what this expression means, right? This is non-zero only if x0 is larger than y0. Then put the x guy later than the y guy. That's what it means. So in this case, you have to write it as x and y. So that's time of rate done. But if, on the other hand, time of y is greater than that of x, then you have to write the other way around. Okay, so that's the meaning of the time ordering. So if you have n number of them, you can have n factorial number of ordering of the times, and each of them just write according to the time order. That's what it means. Now, in quantum field, I said this is an interesting object, and most of the time you will spend working and thinking about this quantity. Okay, so this will give you information about the scattering processes and so on and so forth. But for now, instead of actually telling you other aspects of this correlation function, which we will spend a lot of time the rest of the course, let me just go directly into the aspect of symmetry. So if there is a symmetry which survives to be a good symmetry even at the quantum mechanical level, okay, let's suppose that. You might ask, is there any case where classical symmetry does not survive as quantum symmetry? There's an instance of that, known as anomaly. But for now, let's not worry about that. So this is a good symmetry. Then the symmetry statement about the quantum symmetry statement at the quantum mechanical level reads as follows. So divergence of you could have a lot of other operators. Well, so this is expressed for word identity. Okay, so let me some of the interrupted. Let me write it again. Okay, so this is the expression, but let me let's tell you the meaning of this expression. Okay, so classically we had this clean, nice expression, right? Okay, divergence is zero. So we are looking at almost that kind of expression. So is divergence zero? We're asking that in the presence of other operators. Okay, which can be in principle charged under the symmetry transformation that we are interested in. Okay, so there's a field theory, there's a field, or some operators which can be transforming non-trivially under the symmetry that we are talking about here. Basically, we're asking, is it divergent list as a quantum mechanical expression? That's the question we are asking. Now, if the location of this charge this operator away from the point where I do have a current operator. Now this is operator because I'm looking at the expectation value of the quantum field. So these are all quantum operators. Okay, so we start with the classical thing. We quantized it. We talked about it, and here is all quantum operators. So if this y doesn't coincide with x, meaning it's away from that point, this is 0. Right? It means that it is a divergent list as a quantum mechanical operator language. Right? If you have an operator J, its divergence is 0. However, if that coincides, meaning y happen to be the same point as x, then it's not any more divergent list. But what it does is that it spits out the transformation of that operator. Okay, so that's what this quantum. This is the statement about word identity, which is about incorporation of the statement of symmetry at the quantum mechanical level. But this gives you another very important expression. That's why I even write down this expression. So again, we are not going to derive this today. Hopefully, sometime later, once after we learn the path integral. But let me actually just use it to extract important information. That's what I want to know. So the claim is that this implies that Q of T, now charge operator, now not just charge function, this is charge operator, everything is function, also operator, acting on the charge to object is equal to I slash Y. So this is what I want to derive now. But before I derive this, can you read this equation? I don't mean the bracket of Q with not that way. Can you read this equation? Meaning, can you get the information or physics meaning of that equation? So here's a hint. So if you had some quantum operator in your class, A, so nice operator, and then if you acted by minus I epsilon Q as an operator, plus I epsilon Q, and then suppose this gives you the transformation of that operator. I'm sorry, 1A plus transformation of that operator. Okay? So you have seen something like this, right? There's something acted by adjoint transformation that is transformed operator. If you expand this to linear order in epsilon, you should get an equation that looks like this. Right? You haven't seen this. Or just work it out, okay? After the class. Therefore, the way you read this equation is that, the Q that you construct according to the prescription we worked out today, right? Given a Lagrangian, you know how to construct a Q. That Q is actually performing the symmetric transformation on the field, according to this language. Okay? So that's what that means. You should be surprised or at least happy, right? We said, here's a Lagrangian. I don't know how to perform the transformation on the field, meaning I don't know which operator performs the symmetry action on the field, but if somebody tells me how field transform, I can derive the current, I can derive the charge. But once you quantize, then word identity tells you backward which operator was actually performing the transformation, which is written in terms of the whole field itself. This is completing the cycle. Let me say that again. I give you a Lagrangian made of this field. I just tell you how field transform, but did not tell you which operator actually performs that transformation in the universe space. I just tell you field transform according to this rule. Then you can just follow the prescription, derive current, conjugate the charge, right? That's what we have done. We never ask in the universe space, in quantized theory, which operator actually does the job. we just believed it, right? But now if you quantize the thing, that quantum operator, charge operator, if it is exponentiated, is exactly the thing that actually performed the transformation on that field. Okay, so I said it twice. So that's what this equation means. All right. So then the question is how to derive this. Okay, let me quickly derive this. So let's work this out really quick. I think it's important exercise to do. So the first step is, so let's first consider the single instruction field. So let's look at divergence of vacuum expectation value of a charge current and the operator. So the first step towards this is first let's write divergence of this, which I wrote down the definition of it. Right? So that means x0 minus y0 j. Would you mind if I write it as this? Is that observed? Is that okay? Okay, very good. Okay, so I have written this definition of it. Okay, so let's do it. Let's first, I'm just gonna do it here. I don't want to. All right, so now let's first act this guy on the, remember this is particularly derivative with respect to x. So it can only act here, there, but not on y's. Okay, so that is equal to, so if I just act first on the j's, I get the following. So x0 minus y0. X, y. Okay, so that's when I add the derivative on j's. Now let's also add that guy on the theta function. If I do it, so if I look at the I component of the j around mu, that doesn't add here, right? Because it is derivative with respect to xi, but this is not a function of xi. So that triple x, meaning nothing comes out, meaning 0. So therefore, the only non-trivial expression I get is when mu is equal to 0. Then it acts on here, it can act on here. But when I pick the mu equal to 0, I have to pick the mu equal to 0 here, mu equal to 0 here probably. Okay? So if I do that, I should get the following. x0 minus y0 j0x minus, because the argument. Okay, so you get so far? Okay, good. So what is this? So let's combine. The first line is nothing but time ordered expectation value of that with that. Right, that was the definition. That is just time ordered of this. That combined. The second line, because delta function is an even function, like let's pull it out as this, and then commutator of J0 by 1. Okay, that's the left hand side. Now, before I clean it up, let me just use the fact that as an operator equation, this itself is 0. If one uses, for instance, equation of motion. As an operator equation, I mean. Okay? Or so I mentioned that, I said that because if we just think of the perturbation theory, meaning you have a grid theory, we use at small interactions, and then you just build up the theory. with the small perturbation with respect to free theory, you can just work it out this explicitly using classical equation of motion as operator equation, Heisenberg equation, that's what I mean. Or even there's a non-perturbative notion, meaning without worrying about the size of the coupling, that conserved operator is a conserved operator, meaning this operator just is conserved. Otherwise, there's even a notion of symmetry to begin with. All right, so anyway, that is zero. Let's look at, therefore look at the second term combined with the right hand side. So I just worked at this side. What about this side? So let's work that out. So therefore, this is equal to I times d by 1. Sorry, I forget the delta. Okay, good. Now we are almost ready. So the only thing that I have to do is integrate both sides with respect to d3x. Okay, so the left hand side I get delta of x0 and y0 commutator of now q of t, which is a q t I mean x0, and then this operator. But then because of the delta function, it is enforced that I have to pick the same time. Otherwise, it's 0. Okay, so that's the left hand side. Again, I just integrate. Because this is a non-zero only if time of y is the same as time of x. So I just pick time of y with the same as time of charge. Okay? That should be equal to now this side. So that side, you see, out of the 4 delta function, 3 of them get removed, right? Because of this integration, the only thing that left over is x0 and 0, and then d of x, y, again at the same time. All right. So by looking at that, you can read out the expression that I promised you before. Okay. So again, the reason why I was trying to explain the physics meaning of this before we even derive is not to lose the way. Okay. So this is a technical step. It's good to know, but real meaning is that the quantum operator after quantization, the charge operator actually creates or generates the symmetry transformation on the field that you started with. Question. Okay. Now, yes.
그래서 오른쪽 칸에서 D3x 안에 들어있는 괄호가 저 왼쪽 아래에서 느낌표 오른쪽에 있어요.
Right. So this is left hand side is equal to right hand side. So I'm integrating both sides over D3x. That's what I meant. Okay. Yes.
I wonder whether there is a relationship between time ordering and causality.
Relationship. So first of all, time ordering is a notation, just like normal ordering, to mean something specific. Okay, in this sense, notation. We can ask whether time ordering was introduced in such a way that causality, a feature of causality becomes, I don't know, manifest. We can ask that way, for instance. I don't know if you want to change your question or not, but probably not. But so if I just stick to your original question, whether there's intrinsic connection between the two, the answer might be in general no, because one is just notation, the other is a physics principle. One can define or design the notation in such a way that some feature can be manifest, for instance, right? But you see, so long as we use quantum field that we spend more than 2 weeks to construct, we know that will satisfy causality, modulo some subtle issues. I say modulo because even with this quantum field that you constructed, I told you briefly that depending on the interaction you write down, sometimes you can still violate the causality. But time ordering appears for the reason that I will discuss, probably sometime next week or the week after. Yeah, any other question? Yes.
So do we drop the first equation Tj mu equal I delta first? The
First is this.
yeah.
I have not derived here. I just declare that the quantum mechanical level, which I raised this part, there's a statement about the symmetry, and that statement looks like this here. Just like classically, the statement is like conservation of current. This is the quantum analog of the classical version. And then I just took it and motivated why you may want to look at something like this, but then I just used it to show that it actually captures important information about the fact that you can now see the performance of the symmetry by the quantum operators. Did I answer your question by the way?
Yes.
Okay. Another question.
So is that fine? Why just the backup expectation value you write it there?
Where here?
Yes, so at next line you would only find, so.
Okay, good. So good question. So how you have to read this equation again? Shouldn't read the commutator. You could read it away. So I already gave you one way of reading it. The second way of reading it, this is what's known as operator equation. What do I mean by operator equation? If you insert this in the soup of operator the correlation function, for instance, like if I look at, can I call this to be what's the alphabet like? A. What is your second one? B. Really? So when I say these are all operators, okay? When I say this is an operator equation, what I meant was that suppose you have like all kinds of operators like that. And then in the middle of somewhere you just insert an A, and then it keeps going. Right? Then this must be equal to the exact same sequence of instructions replaced with B. That's what I mean by operator equation. Okay, so if you insert it somewhere in the correlation function, the equality holds. So this is true for every choice of other operator insertions. That's why therefore this should be hold on its own as an equality at the level of quantum operators. Okay? Did I address your question?
Yes.
So I didn't mean that vacuum expectation, but I meant the operator. Okay. Another question. Okay, so I want to talk about the second important aspect of the symmetry, which is related to this. So the second important fact is for continuous. Now here I'm secretly assuming that the symmetry being even quantum mechanically to the symmetry. Then the charge. So far, remember, we have been defining charge operator as integration of J0 components along the spatial time slice, right? So we've been doing that. So and then remember, I labeled like one time slice called like sigma 3, the other time slice like called sigma 3, whatever. So this is in principle, this depends on which time slice I'm integrating over naively, right? Naively, you might think that the charge may depend on which slice you're integrating. In other words, what happens if I kill this? Right? The statement is that for continuous symmetry, charge operator is topological. In a sense that, is this right? In a sense that Q sigma 3 is equal to Q sigma 3 tilde, where sigma 3 tilde is a small continuous deformation of 3, as long as this is important fact, as long as the deformation does not cross charge to for such local operators. I will explain the meaning of this. All right, so let's then think about the meaning of this. So basically, the meaning is the following. If I just, deform this smoothly, continuously, okay, the meaning of charge doesn't change. Okay, it stays the exact same. The only exception is suppose there was this charged operator here. When I deformed it, I accidentally, crossed it like that. Right? Then, oops, I did something radical. Okay? So long as this such a thing doesn't happen, then the meaning of operator, charge operator is identical under any deformation you do. Okay? But the good news is, even if you do this, don't panic, because you know what to do. I just explained to you what to do. If there's a Q of T, there is a charge the guy of Y. When Y coincides with X, meaning you're just crossing it, what do? You perform the symmetry transformation of the charge to the operator. That was the word identity. So now I'm saying, so let's consider the case where you don't cross it, because you know what to do when you cross it. Basically perform the symmetry transformation of the guy. If you don't cross it, then I'm saying Q stays the exact same, no matter what. So let's just quickly prove it. It's very quick to prove it. So let's consider two, therefore, Q of sigma 3 tilde minus Q of sigma 3. Okay? For the sake of completeness, let's consider the following configurations. Here's my charge to object, phi of x. And then I'm surrounding that guy with sigma 3. Okay? So now I'm just drawing as if it is a two sphere, because I cannot draw a three-dimensional guy. Just doing it. And then let's deform it. Let's continuously deform it in such a way that I don't cross any charged operator. So when I deform from here to there, it's clear that I have not crossed any charged operator, right? So I'm just deformed like that. Continuously. Not crossing any charged operator. And then let's call this volume here, there. So by the way, this yellow surface, this one is sigma 3 tilde, and then this volume, the filling between the two, what we call sigma 4 hat. Okay? So the boundary of the sigma 4 hat is the union. Okay, I shouldn't do that. The boundary of sigma 4 hat is this minus that. Right? So let me just write what I just said, and then see if you can do it yourself. So boundary of sigma 4 hat is sigma 3 tilde minus sigma 3. If you are confused, just consider there's a one point deformed into another point P prime connected by the line. The boundary of that thing is P prime minus P. If you, in the sense of integration, right? You take function value here minus of that thing, right? If you do the integration, so that's the sense. But mathematically, what I meant by this minus sign, there's a sense of orientation of manifold, but don't worry too much about it. Okay. So this is sufficient. Now let's actually work it out. This equation that one is for. So that is equal to x tilde integrating over sigma 3 J0 minus over sigma 3 J0. But this can be written as a sigma 4 hat for y, where the boundary is again that minus that, and then this. And for this exercise, I assume that that deformation direction. So that deformation direction is a time direction. That's why I picked up the zero component in the boundary. So there's a one time boundary and another time boundary, just like the way I draw here. Okay, so it's literally like deformed like along the time direction. There's a one time boundary, another time boundary. That's why if I apply the slope theorem here, I pick up the time slice, that's why I pick up the zero component there. Okay? Good, so now I'm done, right? Because this is conserved if it is a symmetry. Then means that this is zero, that means that this is the same for any choice of thing killer. Okay? So in this sense, charge is topological. So once I have a charge operator, then what I can do is that I can now construct what is known as symmetry operator. Symmetry. Sometimes also put defect operator. So this is charge. Then I can construct the symmetry operator, which actually performs the symmetry transformation by which is defined by this. This is known as symmetry defect operator. With a symmetry transformation parameter alpha, and then charge, which is integrated over some surface sigma 3. And now you know that you can pick any sigma 3, right? Just be careful not to throw charge operator. Or whenever you do it, just take into account the fact that you have to transform that operator, right? Otherwise, since Q is topological, obviously it is topological, meaning the meaning of that thing doesn't change under smooth deformation of sigma 3. Now, having said that, let me just say one word. In modern language, in quantum field theory, the notion of symmetry, actually the notion of topological nature of operator actually precedes, meaning is more important than the fact of symmetry. Meaning, whenever you have some topological operator like this, okay, you have an operator in the Hilbert space. Somebody may say that doesn't live in the Hilbert space. I agree with that. If you have an operator, which you check that topological, meaning it doesn't change under the deformation of the spatial surface integrated over, you know that there is associated symmetry already. Okay, so in that sense, topological nature is more important, or is more critical guiding principle in today's business of symmetry in the quantum field theory. Okay, so that's topological. And then now done. I mean, I already wrote down this expression, right? So you have U dagger, I have X, U as an operator equation, you know what? You have symmetry transformation. I already talked about. Okay, so this is full cycle now of a symmetry story. Any question? This may not be super familiar or may sound too artificial or too abstract. Don't worry too much about it. So long as you at least can get this much information. Okay. But this is, I'm just introduced this language. I mean, this is not introduced in the usual like quantum field theory book, but this is the language that actual researchers use today. So I thought I'd just introduce you. Yeah.
What's alpha 2 in the
So alpha, good. So good. Suppose you had a U1 lower, which we'll discuss more next. That means that the element of this thing looks like e to the I alpha. So suppose I call that a G, group element. Okay? So for each alpha, circle valid alpha, there's a group element. And then this guy satisfies group multiplication rule in the sense that G1 times G2 is G1 plus 2. What I mean by that is G1 is e to the I alpha 1, G2 is e to the I alpha 2, and the product of that thing is G to the I alpha 1 plus alpha 2. So there's a group multiplication rule. But this is an abstract mathematics group. And you want to know what is the quantum operator that incorporates this particular transformation on the quantum field. Right? I'm telling you that this is an operator with the same parameter alpha. And you know how to construct this Q now. And this will perform that particular abstract U1 transformation on quantum field. In fact, you can do it even for non-abelian symmetries, which we will discuss next time. Okay, so that's what the meaning of this alpha. So this is a map, if you like, there's a map from abstract group space to a space of quantum operators. This is the construction one can do. All right, so next week we will have lectures. We will go through internal symmetry and then discrete symmetry. And then after that, we will now switch gears to the construction of perturbation theory. Okay, any questions? Okay, if not, we will.